right, so once again, welcome to the Ecology Seminar at Scripps Institution of Oceanography. My name is Tammy Russell, and I'm so happy to present today's speaker, Dr. Stephanie Jenouvrier, an associate scientist at Woods Hole Oceanographic Institution. At WHOI, Dr. Genouvier's lab studies the effects of global change on individuals and populations of seabirds breeding in the Southern Ocean. And she spent the last 20 years researching climate change impacts on invert penguins. And today she'll be presenting climate change threat to the penguin empire. I'll hand it over to you, Stephanie.
Okay, perfect. Well, good morning, everyone. I'm very excited to be here virtually. This is my first virtual lecture. And I'm going to share some new results today, as well as summarizing briefly 2 decades of research on emperor penguin. So let's try why it's okay, perfect. Well, in the midst of this global pandemic, I was reflecting on what has been important in my career and what I am the most grateful for as a scientist. And the answer to this question is working with amazing, smart, kind, and fun people. And I cannot possibly thank all my collaborators and field workers today, as it will take probably the entire hour. However, I wanted to thank briefly my most influential collaborators that enabled me to develop an interdisciplinary research to study the population responses of seabird to climate change. So Henri and Christophe on the right of this slide are seabird ecologists and are supervising one of the most long-term ecological data sets from the tropic to Antarctica. Al and Jimmy are mathematicians and theoretical ecologists developing a complex mathematical model. And Marika is a climatologist focusing on the role of sea ice in the climate system. So my main research interest is population responses to climate change. And those responses are mediated by the allocation and the effect of climate on the feeding and breeding habitat of individuals. So this simple schematic summarizes the complex mechanisms by which climate influence the way individuals acquire and allocate resources. And for example, you can imagine that the weather condition prior to the breeding season may influence whether an individual will have acquired enough resources and be in good condition, body condition to breed. So the effect of climate is thus mediated through this acquisition and allocation processes by modification of the functional trait, or I call functional trait all the traits that relate to physiological condition or behavioral traits such as foraging behavior or mass, for example. And these functional traits affect demographic traits such as survival or fecundity through the decision of individuals they make in investing into reproduction of their own survival, which ultimately affects the population dynamics. And although this conceptual model is pretty simple, it is very challenging to characterize and quantify these links because it requires long-term data set. And so few studies have done so, and especially in the marine environment when it's even harder to collect long-term data set. So this is why I'm studying seabird, for which we have access to long-term data set to characterize the impact of climate change on the population dynamic. So these seabirds are useful and important indicator species for assessing the state of the marine environment. They feed at sea, but they breed on land, so they're relatively easier to study compared to other marine organisms. And because they forage also over very large spatial and they have long-life species, they can integrate the effect of physical oceanographic condition throughout the entire ecosystem. So to study the population response to climate change, I've been developing a three-step approach, which consists of measuring, understanding, and predicting the population responses to climate change. So first, I aim to describe the climate factors that impact the life cycle of a species and the population fluctuation. And to do so, we collect long-term data set and we run some statistical analysis. Then to understand by which demographic processes climate is affecting population, we integrate this relationship we have measured between vital rate, for example, which are breeding success and survival, or the rates that are influencing the population growth and structure. So we include that in mathematical population model, and we are able to understand the processes by which climate affect population. And finally, to predict what will happen in the future, I link this population model to climate model. And today I'm going to illustrate this approach by focusing on one species, the emperor penguin. So the emperor penguin is the only species that bred during the Antarctic winter on the top of the sea ice. And the safe breeding location shown, for example, here by this yellow dot, I don't know if you see the pointer, this safe breeding location can be very far away from the penguin feeding area in open water, like labeled here as polynyas. So I'm going to describe the penguin life cycle, and the penguin arrive at the colony in March, April to breed when after the sea ice has formed. And the female lay a single egg in May. And here you can see the female laying an egg on the picture. And this video is showing how a male are carrying their eggs on their feet, and the eggs need to be kept warm by the male, while the female have left the colony to the nearest open water within sea ice to feed. And by the time the females return, males are fast for 4 months, and they have lost almost half of their weight. And then both parents take turn to feed the chick. And in September, young emperor penguins are left alone at the colony so that both parents can forage together to satisfy the chick's needs. And by December, everybody will have left the colony. And the duration of their foraging trip between the colony and the nearest open water depends on the extent of the surrounding sea ice cover and how far are water openings from the colony. And if there is one thing to remember about the life cycle of emperor penguin, is that there is a Goldilocks zone of sea ice condition for the penguin to thrive. Penguins need water opening within sea ice to feed, but also thick, stable sea ice as a safe platform to raise their chicks. So I'm going to describe now the population responses to sea ice, how we can understand the impact of sea ice on the life cycle of the emperor penguin, which is the step 1 of my approach. So this graph shows the number of breeding pairs of emperor penguin in Terra Deli, which is a colony in East Antarctica here. And this is the only colony for which we have a census every year since the 1960s. And from this figure, you can see that the population was fluctuating around 6,000 breeding pairs in the 60s, early 70s, but then declined dramatically by 50% during the 70s, early 80s, and has remained stable until the early 2000s. I did not update this graph, but the population is slightly increasing, but did not recover to the level prior this huge population decline. And if you look at the sea ice extent in the region around Terra Deli, you can see that this population decline coincide with several years of low sea ice extent. So you can have the correlation between sea ice and the population of emperor penguin, but we were interested to understand the causal links between the influence of sea ice on the population dynamic. So to do so, we need to first understand how sea ice influence the emperor penguin life cycle. And I really like this figure because it really shows what I've described before with the nice pictures and movie of emperor penguin, that basically the sea ice affects the distance and the duration of the foraging trip of adult emperor penguin between, the colony where they breed and the water area within sea ice where they feed. And the sea ice affect how the energetic cost associated with those foraging trips have consequences on the vital rate, such as adult survival of the probability to raise successfully a chick. So the first step is to understand the effect of sea ice on foraging behavior. And I am a population ecologist, so to understand how sea ice influence the foraging habitat and behavior of emperor penguin, I work with Sarah Labous, who did her postdoc at WHOI and is actually now a postdoc at the University of Minnesota. And you can find much more information on her paper that was published last year. So to study the foraging of emperor penguin at sea and within sea ice, we have worked with data where 56 emperor penguin have been equipped and instrumented with a satellite tracker here, shown on this picture. And Sarah did an incredible job by analyzing visible and thermal infrared images showing sea ice fast ice extent from advanced, very high resolution radiometer coastal atlas of East Antarctica. And she did so for two penguin colonies, the Oyster colony and the Point Geologique colony in East Antarctica. Point Geologique is the same as Terra Deli, that for which I showed the population census before. And this figure shows here on the left the continent. The star here is the penguin colony location. And then she found she characterized the fast ice and the pack ice. And this blue line shows the limit between the fast ice and the pack ice. Then she calculated the time spent by emperor penguin each of these pixels. And the red color shows a lot of time spent in an area, while yellow, light color shows not so much time spent in an area. And from this figure, you can clearly see that penguins spend most of their time at the edge of the fast ice here. Not sure we can see very well the pointer, but. So the second part of the question was, do penguins use coastal persistent polynyas? So coastal latent heat polynyas are regions of open water and or region of thin ice, or low sea ice concentration that can be persistent or recurrent. And Sarah used sea ice production to characterize those coastal polynya, like shown here, for example, with this red contour. And the sea ice production is shown by this color bar here from red to green. And she computed, so here on the figure, you can see the continent in black, the colony location in red, and all those blue color just show the time spent of emperor penguin in this area. And it has been previously hypothesized that penguins use large recurrent and persistent polynyas to feed between the fast ice edge and the pack ice as foraging habitat during the breeding season. But this figure shows that penguins did not visit the large yearly persistent polynyas that you can see here. So instead, emperor penguins foraged in ephemeral polynyas opening between the fast ice and the pack ice. or over the continent that are situated in of the figure. For example, show two panels, one in July and August, to illustrate that they are using this ephemeral polynya. So we still have the continent in black, the blue dot is the colony. The fast ice area is this blue area. The big wind track are in red, and this color bar shows the number of days with daily form polynya. So for example, reddish color are openings that open waters that are opening for very few days, like 5 days, while a green color show more persistent opening around like 1 month. So this is, for example, the large polynyas that we have seen that is persistent and open year-round. But all those opening here and here, or even the extension of these polynyas that we did not show, we did not see on the figure previously, are open water that open only for a short duration. So these ephemeral openings are only detectable with fine temporal and spatial scale CS product. And this was a daunting task, in fact, for Sarah to quantify those number of days this water opening are formed using this CS production data, but they allow us to better understand how emperor penguins are using this fine scale feature. And this movie, let me, oh no, so why is, because, do you see the movie running? I think I have to take off the pointer. Supposed to have, let me.
Yeah, I don't see it.
Yeah, it was working pretty. I think it's because I am in this pointer mode, which I don't really know how to take off. Oh, here. I do automatic here. Okay, so I will remove the pointer then. So this movie that Sarah did is an animation to illustrate how dynamic is the CS environment is. You can see the CS production daily that is varying tremendously from day to day. The fastest delimitation here in blue is was done only monthly because we did not have daily data, but you can see it varies a lot from month to month. And the penguin track in the red show how penguin move through this sea escape and use opportunistically those water opening within sea ice. So then the question was to describe how this fine scale sea ice feature affects the vital rate of emperor penguin. And to do so, I have another animation here. Sarah computed the time series of both fast ice, which is shown with this reddish area here. And she computed also the distance between the nearest open water area and the colony in Terra Deli, point geologique shown here by the blue star. And we then related this time series of fast ice and the distance to the nearest open water to vital rate. And for example, here, the upper panel shows the breeding success that was recorded since 1960s, but since we have fast ice data only since 1988, we are showing the time series only since 1988 here. And when you look at the relationship between reproductive success and the nearest open water area, we found a negative relationship. And we also found a negative relationship between the breeding success and the fast ice area. So both the fast ice area and the distance to the nearest water opening illustrate how far emperor penguin have to forage to reach a feeding ground. So when the feeding ground are further, so the foraging distance and duration are increasing, the frequency at which emperor penguins are able to feed their chick decrease, and hence, they have a harder time to raise successfully a chick, and the reproductive success decrease. And I want you to pay attention to this massive breeding failure. During those years, for example, almost no chicks survive. And this, during those years, the fast ice was really extensive. And sorry for the typo here. So we have described the relationship between sea ice and sea ice at fine scale, spatial and temporal scale, and the life cycle of the anthropic wind. I've shown the population fluctuation, but now we want to understand by which demographic mechanisms sea ice is affecting anthropic wind population. So we are developing a population model. And we develop population model because it's very hard to project what will be the impact of sea ice, because it affects vita rate in different ways. So I've shown the relationship between sea ice concentration and fast ice and the distance to the nearest open water with breeding success, and we had a negative relationship. I did not show the relationship we characterized with survival. It was a much more complex, non-linear bell-shaped relationship. But basically what I want to, the point I want to make here is that sea ice is affecting breeding success and survival in different ways. And so predict what will happen at the population size, which is both influenced by both the mortality and fecundity processes, is complex. So to understand better the demographic mechanisms, we build what we call a population stage structure model, which basically separates the population in different classes. So for birds, we use a stage based on reproductive status, because it's very important for long-life species to include the fact that they breed for the first time when they are quite old, like for 4 to 5 year olds. So they spend a lot of time as prebreeder, individuals that have yet to breed. And then they can form a breeding pair and breed during a season, but they also can skip breeding. So non-breeders are individuals that have bred at least once before in their life, but skip breeding that year. So we include this class of individuals in a population vector, and we project the population from time t to t+1 using a population matrix A that include all the relationships that we have estimated between sea ice and vita rate, other environmental factors. And also here we have nonlinear effect because we are accounting for mating processes. I'm not going to enter into the detail of this demographic model. Just want to answer to a few important questions you may have. You may ask, why the population declined by 50% during the 70s, late 70s, early 80s? And using this demographic modeling, we found that it was because adult survival of male decreased during that period. And the adult survival of male is lower than the adult survival of female, and male are survival of male are affected by sea ice. And we interpret those results in the light of the fact that males have to fast for 4 months during the breeding season. So they are more sensitive to sea ice variation that control the access and availability of resources. The second question you may have is why the population did not recover after the 70s, 80s, while adult survival increased back to the level before the population crash. And what we found, so this is a kind of a complex, overwhelming slide, but what we found is that sea ice is influencing the breeding success, and higher frequency of massive breeding failure have prevented the population to recover. And to illustrate that, I show here the mean and variance of breeding success across several decades. And you can see that the mean breeding success decreased from 72% to 46% for the decade from the 90s to 2000 year. And the variance increased. And from this graph, you can see that we have seen much more massive breeding failure occurring during those decades. And using simulation, we have been able to show that this increase in this massive breeding failure event have prevented the population to recover. And if you remember, they were linked to years with extensive fast ice. So to summarize and explain the population dynamic we have observed in Terra Delhi, we have shown that the dramatic decline in the 70s, 80s was driven by higher mortality of male that was related to low sea ice concentration during those years. And then the population did not recover because the colony experiences more frequent massive breeding failure that are related with years with extensive fast ice. So now I'm going to talk about how we can link this population demographic model to climate model to project what will happen in the future. And I don't know if you hear my kids, but I'm sorry. With the confinement, we have to manage, balance family life and working life. So sorry if you hear them yelling on the background. But I wanted to show this graph, although you may probably all know that already. But I found this graph very powerful, especially if you pay attention on the x-axis that is goes back to at least 3 million years ago. So this graph shows that today the carbon dioxide in the atmosphere is well above anything we have ever experienced as human. And under business as usual scenarios, if greenhouse gases concentration continues their current course, the carbon dioxide in the atmosphere is projected to reach 950 parts per million. So I think it's crazy. And when we look at how it will impact sea ice and the onpropping wind, this will have dramatic effects. So this figure shows the number of breeding pairs we have shown already before that we have observed the last 60 years. And the projection we have made by linking this demographic model with a model, climate model that was developed by NCAR under the business as usual scenario RCP 8.5. And under this scenario, the median, which is this red line here, of the population projection is projected to be extinct by the end of the century. And we have accounted for many uncertainties related to demographic and climatic processes. And those uncertainties are characterized by this envelope here. So you may say, well, this is in Terra Delhi, it's one onpropping wind colony here in East Antarctica, but we know that sea ice is projected to decline at different rate according to different region. And for example, in the Ross Sea, here the decline will be much more smaller than other regions by the end of the century. And we know that there are 54 penguin colonies around Antarctica. So this map is showing the location of this emperor penguin colony. Terra Delhi is here. And this work has been done from satellite imagery by some of my colleagues. And I want you to pay attention to those yellow dots now. I'm going to show what will happen in the future. And when you look at what will happen in the future, most of these yellow dots have disappeared under business as usual scenarios. 80% of the colony will go extinct by the end of the century. And importantly, the few colonies that will have not disappeared, shown in yellow here in the Weddell Sea and in the Ross Sea, will be declining. That means that there will be no viable refugee by the end of the century for emperor penguin. And because Antarctica or the world emperor penguin colony population, this means that emperor penguin are marching towards extinction. So you will say, well, this is under a business as usual scenario, but we are trying to implement some climate policy, and specifically the Paris Agreement, which is a multinational initiative to curb future atmospheric warming, with a goal of limiting the global temperature increase to well below 2 degrees Celsius and ideally to 1.5 degrees Celsius or about 3 degrees Fahrenheit relative to the pre-industrial mean. So would this climate mitigation help to prevent the extinction of emperor penguin? So to address that question, we did the same thing. We link our demographic model with climate modeling and use different climate scenarios, including scenarios of the Paris Agreement. And this animation is looping between the business as usual scenarios and the different Paris Agreement run. So here is the business as usual scenarios with 80% of penguin colony disappearing. Now it's going too fast. So this is a business as usual scenario. Now we have the Paris Agreement target 2 degrees, and the last one is the Paris Agreement 1.5 degrees. So if the world would take aggressive action to reduce the greenhouse gases emission and the Paris Agreement objectives are met, viable emperor penguin refuges will exist in Antarctica by the end of the centuries. And the model still project decline. Some colonies are still going to be extinct, but the trend will be much less severe and fewer colonies will go to extinction. And for giving you some numbers, under the Paris Agreement 1.5, only 10 colonies, which is about 19%, are going to be quasi-extinct by the end of the century. And with the Paris Agreement 2 degrees, it's 30% of the colonies that are projected to be quasi-extinct. And this figure shows the global population size of emperor penguin colony. So we have in red here the projection of the global population size under business as usual scenarios. And under these scenarios, the global population is projected to decrease dramatically, resulting in an annual decline of about 4% per year at the end of the century. And if you calculate the time that is required for the population to decrease in half by the end of the century, this half-life is 17 years. So that means that under this condition, the species will go extinct rapidly. However, if you look at the blue line and the red line here, which shows what we will obtain with climate mitigation, under the Paris Agreement, the population growth rate stabilized at the end of the century. They are slightly declining, but at a much lower rate. For example, under the Paris Agreement 1.5, the population is only declining by 0.07%, and it corresponds to a half-life of about 1,000 years. And under the Paris 2 Agreement scenario, the half-life is about 200 years. So meeting this Paris Agreement will allow us more time to implement more climate mitigation and conservation strategy, and will avoid the march to extinction for the emperor penguin. So I'm going to skip that part because I realize I will have no time, but you may ask, well, what about, the adaptive or dispersive capabilities of emperor penguin facing climate change? Because we know that in the past, many plants and animals reacted to environmental changes by either adapting, migrating, or going extinct. So to avoid extinction, they might be able to move elsewhere, and this might help this might help the persistence of the species by tracking their preferred habitat condition. I'm going to skip the description of the model. I'm going to jump to this 3 panel I'm sorry, we don't really see much as a difference in terms of the color line, but basically it shows a main point, which the 3 panels showing the different climate scenarios. We have the global population size on the y-axis, so for the business as usual scenarios and the Paris Agreement 2 and 1.5 degrees. And the different line here show scenarios with no dispersion or various dispersive strategies that relate to different dispersal distance or different type of behavior. But basically it shows that when you look, there is not much difference between those dispersive scenarios, while there are huge difference between the climate scenarios in terms of the total population size projected by the end of the centuries. So the main conclusion here is that global policy has a larger capacity to safeguard the future of unpropping winds than their intrinsic dispersal abilities. So I talk here about movement, and as I say, individual can adapt, move, or die. So what about adaptation? So this is where it's very important to develop this eco-evolutionary approach to understand better how climate can influence the population dynamic. But that requires to have information on both how the climate affects functional traits like physiological or behavioral trait and the demographic trait. So very few studies have been able to make those links, as I said before. And unfortunately, for the unpropping wind, we don't have enough data to make those links between foraging ecology and demography. So we are not really able to answer that question and see if unpropping wind can adapt to future climate change. But we believe that given they are a long-lived species, there is probably few possibilities by which it can adapt to the fast changing climate. But I'm hoping that next year I will be able to come to Scripps in person to talk about results that some approach I'm developing to study how species can adapt to climate change. And I'm going to illustrate some work we have done on albatrosses, for which we have more information and we are able to make those links between body condition, foraging behavior, climate, and demography. And just to give you a test, there are very preliminary results, so they will probably change between now and next year. But this, for example, graph shows the population size that is projected again until the end of the century under 2 scenarios. One scenario where individuals are not able really to change in a specific way their foraging skill, and a scenario where they are able to improve throughout their life their foraging skill, and they're also able to transmit their foraging skill to their offspring. And in that case, the population decline is delayed by 30 years. So accounting for these eco-evolutionary scenarios are very important if we want to understand better the processes by which species can respond to climate change, but also in terms of conservation, how much we can gain in terms of time to delay population decline and implement mitigation strategies, for example. With that, I would like to conclude that emperor penguin and on all species on Earth, including us, face very different futures. So we really need to take action if we want to avoid dramatic impact of climate change on emperor penguin and many other polar species and other species. And we also need to improve our understanding of these eco-evolutionary mechanisms by which species can respond to climate change to better project and improve our ability to forecast what will happen by the end of the century. And with that, I would like to thank all colleagues and field workers that have been involved in the research on penguins since 60 years. And my sister Aurélie, who have provided all the unique watercolor and cartoon shown in this presentation, and all the funding that have allowed me to support that work during the last 2 decades. Thank you.